good. I don't see any questions popping up. So we're going to move on now to speak about the Starling forces that govern the movement of this protein-free plasma across the filtration barrier. So you would have talked about the Starling's forces with Dr. Schlater. You would have talked about these equal and opposite forces that are either hydrostatic, which is pushing, or oncotic, which is pulling, and this dictates the movement of fluid, plasma to be specific, from the glomerulus here, which are in these endothelial, which are in these capillaries, into the Bowman's capsule. Okay. So let's describe the four forces first. And it's a very similar phenomenon as what you would have talked about in terms of movement of fluid across capillaries. Same thing happening here. But let's describe the forces first, and then we'll talk about what direction they're moving in and practice some calculations. So the first force is the glomerular capillary hydrostatic force. And this is a push force, which is indicated by hydrostatic, which is happening from the capillary across into the Bowman's capsule. So the glomerular capillary hydrostatic force wants fluid to go from the glomerulus into the Bowman's capsule. This is a push force that is created by the fluid that's present in this capillary. Second is the Bowman's capsule oncotic pressure. So the Bowman's capsule oncotic pressure is going to be a pull force, and we know that by the term oncotic, which is interchangeable with osmotic, right? You can think about those as being the same. And this is a pull force that is represented by the presence of proteins. So just going back a little bit to what we talked about last semester, if we've got more proteins present on one side of a membrane that is not permeable to the proteins themselves, then in order to equalize the concentrations, fluid is going to move from the area where it's in high concentration across to the area where there's more protein. And so we can say that the presence of proteins on that side of the membrane pulls fluid towards it, and that is what we mean by the oncotic pressure. The ability of proteins to pull fluid to the side that they are located in. So the Bowman's capsule oncotic pressure is a pull force that's pulling fluid from the capillaries, from the glomerulus, into the Bowman's capsule, and this is always going to be zero. Okay, this is always going to be zero simply because proteins are never in the Bowman's capsule. I want you guys to make a note of this in your notes. The Bowman's capsule oncotic pressure should always be zero because proteins should never exist in this space. Because, as we just talked about, proteins are too large to be filtered across the glomerular membrane or the filtration membrane. And so although we want to take into account this force, we want to also understand that it should always be zero because there aren't any proteins in the Bowman space, or there shouldn't be. Okay, if we get into some of the kidney disorders where there's disruption to this membrane and proteins start to spill into the urine, that's where you may see differences here. But under normal, healthy circumstances, there should be no protein in the urine. There should be no protein in this space. So this value, the Bowman's capsule oncotic pressure, should always be zero. The third force is called the Bowman's capsule hydrostatic pressure. So this is another push force. Again, we know that by the word hydrostatic here. And so this is a force that wants to push fluid from the Bowman's capsule back into the glomerulus, back into the capillaries. Okay, so this is going to be directly opposing the glomerular capillary hydrostatic pressure. And then finally, we've got the glomerular capillary oncotic pressure, which is another pull force. And this wants to pull fluid from the Bowman's capsule back into the glomerular capillaries, and that is going to be a representation of the amount of protein that's present in the capillaries here. And as we should know, there's lots of proteins that remain in the capillaries, and so we're going to have a positive value for the glomerular capillary oncotic pressure. Okay. All right, so here we can see a little kind of a description of the values that are associated with these forces, but we're going to draw it out so that you can kind of follow along and just make sure that we're making sense of this. All right, so we've got the glomerular, oops, my marker kind of dried out here. So we've got the glomerular filtration pressures. Okay, and let's start by drawing our afferent and efferent arterioles. So here's our afferent arteriole. Here's our efferent arteriole. Okay. Here's our glomerulus, this ball of capillaries, which is basically a modification of these arterioles. And then here is our Bowman's capsule. Oops. So here's our visceral layer, our parietal layer, and then we've got the remaining tubular structures. So we're really focusing on what's happening across this filtration membrane. So let's label this out here for clarity. This is our Bowman's capsule. And this is the glomerulus. Okay. We spent some time describing the 3 layers of this membrane. So this is that filtration membrane that we were speaking about. So I'm just going to label it out here. Filtration or glomerular membrane. All right. So the forces that we're speaking about are acting across this membrane. So we've got the glomerular capillary hydrostatic pressure, which is the first. Let's get another color. So this is the glomerular capillary hydrostatic pressure. And we're going to represent hydrostatic with a large P, and then glomerular capillary with GC. So I hope you understand what that means. So glomerular capillary hydrostatic pressure, and this is a push force. And because it's moving from the capillary into the Bowman space, this is favoring filtration. Okay. Then we talked about the Bowman's capsule hydrostatic pressure. So that's also going to be a large P. Bowman's capsule hydrostatic pressure. This is also a push. But because this is a push from the Bowman's capsule back into the glomerulus, so in this direction, this is favoring reabsorption, or this is opposing filtration. Okay. So these are our 2 hydrostatic forces. One is pushing from the glomerulus into the Bowman's capsule, that favors filtration. One is pushing from the Bowman's capsule back into the glomerulus. This is opposing filtration. Let's talk about our oncotic pressures. So we've got the Bowman's capsule oncotic pressure. So this is the symbol that we represent oncotic with, and this is of the Bowman's capsule. And we know that this is a pull force. Oops, only 2 L's. This is a pull force. And because it's pulling fluid from the glomerulus into the Bowman's capsule, so this direction, this is going to be favoring filtration. But remember we said this is always 0. Okay, make a note of that. Always 0. And we described why, because there aren't any proteins in the Bowman's capsule, so there should be no oncotic pressure pulling fluid from the capillary. The second oncotic force is the glomerular capillary oncotic pressure. This is also a pull force, but it's going to be pulling fluid from the Bowman's capsule back into the glomerulus. And because it's moving in this direction, this is going to be opposing filtration. Okay, so we have two forces that favor filtration, our glomerular capillary hydrostatic pressure and our Bowman's capsule oncotic pressure, and then two forces that oppose filtration, which are the glomerular capillary oncotic pressure and the Bowman's capsule hydrostatic pressure. Okay, so I really want you to take a second and make sure you understand why these forces favor or oppose filtration based upon the direction that this force is moving in. Okay, and let me see if there are any questions that pop up. It's really important for you to understand each of the forces and what direction they're moving in. Okay, so let's plug some values in here and let's do a bit of calculation and see what we come up with. So typically our glomerular capillary hydrostatic pressure is about 60 millimeters of mercury. Okay, our Bowman's capsule hydrostatic pressure is about 15 millimeters of mercury. And this should make sense, right? There's more fluid in the capillaries than there is in the Bowman's capsule. So we're gonna have a higher hydrostatic pressure in the glomerular capillary than we do in the Bowman's capsule. The glomerular capillary oncotic pressure is about 29 millimeters of mercury. And we know that the Bowman's capsule oncotic pressure should always be 0. Okay. And based upon our overall formula for calculating the glomerular filtration pressure, that is basically our forces that favor filtration minus our forces that oppose filtration. Okay, so we want to identify the forces that favor filtration. So that's going to be our hydrostatic glomerular capillary pressure. So that's going to be 60. And our Bowman's capsule oncotic pressure, which is 0. And then we want to identify our forces that oppose filtration. So that's going to be our Bowman's capsule hydrostatic pressure, which is 15, plus our glomerular capillary oncotic pressure, which is 29. Okay, so that should give us 60 minus 44. So that's a grand total of 16 millimeters of mercury. Okay. I want you to be very, very clear in understanding how we got this in terms of our overall net glomerular filtration pressure. Okay, being able to identify the filtration forces, being able to identify the forces that oppose, and then doing the simple math that follows.